Good morning, everybody. Welcome to this. This is going to be a little bit different from Steve's presentation in that I was with a water utility. So I'm going to be looking at it from the perspective of one of the organizations that would have provided information to Steve in his survey. In my presentation today, I'm going to provide some background information. I'll talk about the water distribution system history in Edmonton. And then I'll talk about some different pipe materials and also our PVC pipe materials experience in detail. We undertook a number of testing programs on PVC pipe over the last number of years. And particularly, I'll go with the 40-year test. So Edmonton was the first water utility to use PVC water main pipe in Western Canada. And in 2017, we dug out some of that original pipe. And we then tested that against the expectation for a brand new pipe coming off the assembly line. And I'll conclude with some performance comparisons for water main materials and our experience with that. So I graduated in 1978 with a Bachelor of Engineering degree, and you've heard about some of my history already. I joined this city's water utility in 1988, and I was mainly responsible for transmission main projects at that point. But by 1994, I was asked to add distribution projects into my portfolio as well. And through that, I tested a number of different water main materials, and PVC will be the one that we'll talk about mostly today. I've been retired now for 5 years from that utility. A bit of background on EPCOR. EPCOR Utilities is a utility in Edmonton. It's formerly all city departments that were set aside and put into a private organization. And they look after water treatment and distribution, wastewater collection and treatment, electrical power transmission and distribution within Edmonton. It's wholly owned by the city. It operates not only in Edmonton, but also in other parts of Canada and the United States. So if you were in Arizona, you would be quite familiar with it. They're the largest private water utility in Arizona, and also in New Mexico, and they also have a presence in Texas. In Ontario, in Canada, they also look after some natural gas distribution as well. As far as the Edmonton area, the large yellow, dark yellow section in there is the city of Edmonton. You can see the two red water treatment plants within the city, and then you'll see there's a very large light yellow area around that. That light yellow area contains about 10 different regional water authorities that are customers of EPCOR Water, and they distribute water to 70 plus different communities, some of them up to 125 miles away from Edmonton, but they distribute water that's treated at Edmonton's water plants. The province of Alberta decided they would rather do it that way and support these regional water authorities so that they would have good quality water to provide to their people rather than have a number of very small utilities spread out across the north with staff that may not have the level of expertise necessary to provide the safest drinking water to people. So just in the public health interest, they decided they want to go that way. Edmonton started off as a Hudson's Bay trading post many years ago. The photographs here are from a historical park, and of course they're just recreations of what things probably looked like at that point in time. In Edmonton, in the foreground in this photograph, you'll see the original water treatment plant, and it has been, of course, updated and changed since 1902, but that's where it was located. It was right on the North Saskatchewan River, and that is the primary water source for Edmonton. This North Saskatchewan River flows through the entire city. In the summertime, it looks pretty good. As we get to winter, it's somewhat frozen over and cold. So it's very different from the weather that you would expect to see here. Winter does definitely come, and when it does, there's a big change in the temperatures. You can see on the numbers here that from winter to summer, things change quite a bit, but also the water source, the river. In the wintertime, it's just about solid. It's just above the freezing point. And in the summertime, it gets up to be quite a bit warmer, so it introduces some treatment challenges with that variation in temperature for our treatment plants. The soil that our pipes are buried in is predominantly a clay. It's highly corrosive. It's quite highly expansive clay, and so it's susceptible to changes in moisture conditions. So you will notice on some of the slides later, I'll show you where you can see that there's been periods of drought and periods of a lot of water, and in those periods, the break rate does change for some pipe materials. Right at the end of that, you would have seen that we have about 8 feet of cover on our pipes, so it's much deeper than what we're talking about in this part of the world. 1902, these systems started with cast iron, steel, and wood stave pipes. Cast iron was the prominent material choice from the inception of the water utility until about 1965. From 66 to 77, asbestos cement was the predominant material, and after 1977, PVC has been the predominant material that has been installed there. So over 90% of the pipes in service today are either cast iron, asbestos cement, or PVC. And the remaining 8% are steel, concrete cylinder, or HDPE. This shows the the biggest material sections we have. And you can see how the river goes from the southwest to the northeast, and you can see how the city developed with the red pipe in that area, and that's the iron pipe. Then there's a bit of a ring of the yellowish asbestos cement pipe around there with the PVC towards the outside. What you will perhaps notice is right over in this area where a lot of the red pipe is turned blue. And that's because of the replacement program for the iron pipe, as it has caused a fair amount of problems. Between 1902 and 45, as the city grew, sand or pit cast pipe was put in. So that was a pipe that had a very thick pipe wall. And that was one of the most common materials available in North America for water distribution. Edmonton used an unlined version of that. But because of the thick pipe wall, the fact that it was experiencing some corrosion, it didn't show up. The breaks weren't happening, there was no failure, there was no corrosion of the pipe right through. So it was deemed to be a very reliable pipe material. After the Second World War, the city started to grow, partly due to the amount of immigration from Europe, but also because oil was discovered just south of the city in 1949. And that began essentially an oil rush in Alberta for the next many years. They had gone through a transition from that sand cast or to a pit cast to a spun cast pipe. It's a technology that had been developed during the 1930s. And the primary thing was that it had a thinner pipe wall than the sand cast. So that meant that it was cheaper to produce, it was a little bit lighter material to handle, and so it was considered to be a technological advancement. Because the city was growing, the city undertook a report from a consultant to just talk about the water system and give them some guidance as they were growing and selecting pipe materials. And that report confirmed that iron pipe was the way to go for them at that point in time. This was in 1950. Now, basically, as the city grew and they put that spun cast in, they started to see some problems on that pipe. From 1952 to 1965, the system doubled in length, but the number of failures increased tenfold. But the failures they were seeing wasn't on that old pipe that had been put in between 1902 and 1945. It was the pipe that had been put in after 1945. So it was the spun cast pipe. So this pipe was failing within a few years of its installation. We're not talking 53 years like Professor Barfus alluded to in his report. This was within 5 years or less that the pipe was failing. And this is basically a ring of spun cast iron pipe that was in our system. You can see how the external corrosion has taken a lot of the pipe wall away. At about 6 o'clock, you can see where the corrosion has gone just about all the way through the pipe. It just hasn't fallen off, essentially, at this point. But so the corrosion was very hard on the pipe. So in 1966, the city made the transition to asbestos cement pipe. They decided they had to go to a non-metallic pipe. Now, it had been introduced to North America about 1928 or 29, originally developed in Europe. In Edmonton, they were fairly early adopters of it, and in the early 1930s, they started putting a little bit of that in, and they did have some installations that performed quite well. I did take out some of that pipe that was put in 1931, about in 2016. It finally got to the point where it had some failures occurring on it, and so I removed that. Now, the pipe in Edmonton performed well. One thing of interest is that when the Alaska Highway project was built, the American military came to town and based the project out of Edmonton. So that around the downtown airport in Edmonton, they built a number of housing units for military personnel, and so they've serviced all of that with asbestos cement pipe. And that pipe is still in service today. Yes, you have a question?
Yes, going back to the cast iron pipe, back then they didn't coat it or wrap it or have cathodic protection, correct?
There was no cathodic protection put on it. It would have had the sort of that coal tar coating on it that would have come out of the factory, but that would have been the extent of any kind of corrosion. At that point in time, corrosion protection wasn't highly common and wasn't talked about or deemed to be necessary most of the time. So the distribution system grew quite quickly between the 1965 and 1980. That was partly due to the amount of growth in the oil industry in Alberta through the 1970s. Asbestos cement has been a consistently relatively low failure rate material over time, but the problem with health concerns, particularly asbestos airborne fibers from working with the pipe, led the city to look for an alternative pipe material again. Now this is from 1970 to 2018. This shows the annual number of failures that have occurred on asbestos cement pipe in their system. And you can see that it's been a little bit up and down through the years. That's really going with the periods of drought and the periods of higher rainfall. So as the clay that the pipe is buried in starts to change differences in moisture content, it starts to have some shifting and some moving, and that leads to failures in the asbestos cement pipe as the stresses change on that pipe. The first installation of PVC was put in 1977, and that was the first installation in Western Canada. By 1979, it was pretty much being solely installed with no more asbestos cement pipe being used. The pipe that was used was manufactured to C900, AWWA standard, and it was generally a DR18 pipe with bell and spigot jointing. Currently, there's pipe up to 36 inches in diameter in service in PVC in Edmonton, and the larger pipe is certainly not a concern in any way. We've tried a different few forms of this. We've used restrained joint PVC pipe. We've used pipe similar to what you have the opportunity to look at outside here with the FlexLox joint with the nylon piece that goes around to hold it in place. We've used fusible PVC pipe. All of them have performed well for us. No problems with any of those kind of jointing systems. PVC has a very low failure rate in our experience as well. And today in Edmonton, there is more PVC pipe in its distribution system than all of the other materials added up. The first standard for PVC pipe came out in 1975, so it was just 2 years after that first standard was approved that the pipe was used in Edmonton, and it was used in a new residential development that was just occurring in the southeast of the city. 6, 8, and 10-inch diameter pipes were the pipes that were installed in that project. In 1994, seeing that we were using a lot of PVC and wanting to understand how it is performing, we went out and we dug up a little bit of that pipe from 1977, and we took it to the local pipe manufacturer's quality assurance lab, and we put it through the same tests that brand new pipe goes through when it comes off the assembly line. We wanted to see how does this compare to the pipe that's coming off today. So we looked at dimensions of the pipe, extrusion quality, some pressure testing. We looked at the gaskets. We looked at the flattening on that pipe, and also we looked at the Canadian standards test that is a requirement in Edmonton in addition to AWWAC 900, and that's a low temperature impact resistance. And that's really a test that's undertaken to confirm the pipe's durability during installation in winter temperatures in Canada. When you start to get pipe installation occurring in temperatures well below 0 Fahrenheit, there's concern about whether or not those temperatures are going to affect its brittleness when it comes to maybe a little bit of rough handling during the construction process. So that's really what that test is intended to replicate. And then we also did some service tapping of the pipe. So we used direct tapping in Edmonton on our PVC pipe. And so we did some service tapping under pressure as well. In 1994, we tested the 8 and 10-inch pipe. There was no evidence of deterioration, and the only thing that we found was with the extrusion on the pipe. It was a very old, well, today it'd be an old extruding equipment, but it was not as, I guess, sophisticated as the equipment today in terms of the ability to keep the pipe walls the proper thickness. So there were, in a couple of cases, there were some pipe walls that were just a little too thin. Of course, the equipment today is much more refined and able to maintain those dimensions far better. Everything looked fine on that pipe, and I went to the American Water Works Conference in 1998 and presented a paper on that, just to... How many tests?
Yeah, like in 1994, like how many locations?
We tested 2 separate locations. And we had enough pipe to be able to do all of the tests that were required by C900 and the CSA standard as well. In 1993 to 1995, we undertook a different kind of project. We looked at comparing different backfill materials for pipe, and of course we were using PVC pipe at that point, so the PVC was the pipe that was put in. So we looked at the native clay, we looked at sand, an unshrinkable fill, which is basically a very lightweight concrete. We looked at a expanded clay shale insulative product. We looked at some ash from a coal-fired power plant and some concrete that has a lot of air in it, so it's very lightweight. And then we looked at styrofoam board with sand backfill as well. And the idea was that we would put temperature monitoring equipment down every foot down to 8 feet. We would put strain gauges on the pipe, and then we also put in a parallel pipe for part of this installation that had only 3 feet of bury on it instead of the standard 8 foot. We wanted to try and see if the water would freeze in that shallow pipe, and it wouldn't freeze as long as there was a little bit of water moving through it. It just didn't freeze. So by the time we got to the 3rd winter, we'd figured this out, and we closed the valves on the shallow section, and it froze. So that gave us something to think about. So the strain gauges on that shallow pipe indicated that the pipe had expanded to the point that it probably should have broken. It should have exploded, basically. So we waited till spring, we pressurized everything, but nothing was leaking. So we dug out some of that shallow buried pipe, took it over to the lab and put it through a pressure test, and it still required over 1,000 PSI to fail. So that suggested to us that if we have some catastrophic event where we have a freezing incident that occurs on our system, we can probably wait for it to thaw out and it'll be fine, and we'll be able to carry on with minimal damage or maybe no damage to the system.
Could a pipe like be frozen even under 8 feet?
8 feet? We have not seen the frost get down that deep. Typically the frost gets down to about 6 feet, but then we have water services come off the top of the pipe and they have a gooseneck that comes up and then goes over. We want to keep the top of that gooseneck below the frost line because that the service to people's houses is not constantly flowing. And so it's susceptible to freezing when they're not using water. And so we do need to be cognizant of that fact in the design of the system. In 2005, we did another test. We just took pipes that had 25 years of service. And we did all the same kind of testing again. And the bottom of this slide just has a little bit more detailed on that impact test under cold temperatures. So that just explains basically that you take 5 samples and none of the 5 can fail. If one of the 5 fails, you do 5 more and the next 5 need to pass. And if they don't pass, then the pipe does not pass the test. End of story. So there's not a lot of opportunity for problems or failures with those. And the pipes tested fine. There was no problem at all at 25 years. In 2012, we undertook a different kind of a test. We had a company in Toronto that said that they could do sort of long-term pressure simulation. So what they did with that was they took what kind of pressure surges does your system normally operate under. So we gave them some numbers based on our SCADA system. And they then took that back to the lab and they undertook this very rapid cyclic pressure on the pipe to simulate long-term pressure fluctuations on the pipe. And based on that estimation, because pressure surges on plastics do have an impact. Larger pressure surges can have obviously bigger impacts, but they came back to us and said, well, the pipe's likely going to last at least 100 years based on the operating conditions that you have it under. But if you see at the bottom, our SCADA data was only every 5 minutes between pressure instruments because they were not looking for that kind of detail of information. They just were looking for general trends in the system in their SCADA. So I went back the next year and I bought different data loggers and pressure monitoring equipment. And I went out on the system and I got pressure monitoring in 4 different locations for every second for the year. So give me a better indication of what kind of pressure fluctuations are we experiencing. My thoughts were that if there is something that's happening in the operation of the system, the way people are turning pumps on and turning them off, and that is giving us greater pressure fluctuations than what the SCADA system happens to pick up, we probably should change how we're operating our system. It's better to change it now than to wait for 50 or 60 years and find out that if only we had changed it, the pipe would still be lasting. And so I thought it was prudent that we should do that.
Were there some surge events in 2016 and 2017, like a power failure or something?
We did not see anything dramatically different from what the SCADA system had been picking up through the years. So we felt that was fine, that's good. But we also know that operation of the system, sometimes the pumps are not operated the way that they could be operated optimally. And when that happens, we have cast iron water main breaks. So we've had certainly quite a number of cast iron water main breaks through the years that could be attributed directly to how somebody was operating the pumps. On the very big high pressure pumps that come out of the treatment plants themselves, yes, there's surge protection equipment on those, but there's also, we have pumps at reservoirs and things like that that are coming on at different times as demand changes through the system over the course of the days. So essentially, because I didn't determine that there was anything different than what we had estimated when we did the testing with the JANA laboratories in Toronto, we concluded that we're probably okay in terms of the operation of our system at this point in time. In 2017, we went back to that original 1977 installation, and the pipe is now 40 years old. So we went back there and we removed some pipe. Before we did it, of course, we did some more direct taps on the pipe. We did test those direct taps using a dye penetration, and we took the gaskets to a gasket manufacturer's laboratory for testing. We went to a PVC pipe manufacturer's R&D facility and did cell class testing on the pipe and looked at water quality in the system where the PVC pipe was as well. The C900 testing, just to remember, is the extrusion quality, flattening, joint leakage, joint pressurized failure, quick burst test. Everything passed except the flattening test on the 10-inch pipe. So on the flattening test on the left side, you'll see they do a fairly extreme amount of flattening on the pipe to see what it is. On the 10-inch pipe, if you look on the right side, you'll see that blister on it. That blister means that the pipe failed. But this is after 40 years, and it's after it's been flattened out a fair amount. So it's not likely you're going to see that in the field in a pipe that's been buried for 40 years, but that is what the test is. We did the testing to the Canadian standard for the cold weather. And here where things got a little bit maybe confusing, the 10-inch pipe passed the impact test this time. So the ice bath impact test, it passed that, but it failed the flattening test. The 6 and 8-inch pipes failed the impact test, but they passed the flattening test. So it's not consistent on all of the different pipes. But I'm going to talk about the significance of both of those pipe failures a little bit later on here. When we were looking at tapping that pipe under pressure, we wanted to see, is there any damage, any microfracturing or anything like that occurring in the pipe when you're putting that kind of stress on it after 40 years. We did not determine that there was any problem with the pipe at all and being direct tapped after 40 years. The cell class testing was undertaken in Toronto and look at a number of different properties of the pipe to determine if it has the proper class. We also did some microscopy of the service tap location again. So we're still looking at those service taps. We wanted to look and see could a high intensity microscope pick up any kind of microfracturing or anything, because we were just wondering about the stresses of the pipe. Cell class testing, this is some of the equipment that's used and some of the samples as they've gone through that testing process. If you have questions about what cell class testing is all about, there will be a representative here this afternoon from the PVC Pipe Association who will be able to give you much more detailed information than I'm able to do that, so I'm just going to defer that right now. So what happened was the samples that were tested for cell class, there was one failure. It was called a notched IZOD test, and it was 10 or 6.5% below the minimum requirement for it. In terms of the tapped service, there was no evidence of microfractures, but because of the sawtooth pattern that seemed to be evident on some of the threads, it's likely uneven pressure that was applied during that direct tapping process. So that's the skill of the operator of the tapping equipment. Different areas redevelop and change. There may be a need to go back and to put in services. And if we have to put in new services on the pipe, we'd like to have the assurance that we can go back and use the type of system for installation that we commonly use there, because that's what the contractors are accustomed to using. And we saw no reason for us to change our processes at all. With the rubber gaskets, we took them over to Hamilton Kent's manufacturing facility just outside of Toronto. And the test passed everything that would be expected of a new rubber gasket except for the ozone resistance. And the ozone resistance is when there's a problem with some cracking in the material. This is just a list of the different tests that they would have looked at. And the bottom one at the bottom with the X beside it is that ozone resistance, and it was due to cracking. The cracking, this is the 6, 8, and 10-inch gaskets, and you can see that the 6-inch gasket is fine. The 8 and 10-inch aren't. They've got some cracking that's occurring on the outside there. That cracking was considered to be due to exposure to petrochemical. Now, this was farmland. It was not an industrial site that had been redeveloped or anything. So when you look at the cracks, you'll see that they're not very deep at all into the pipe. It's very superficial. So my expectation on this was that during construction, somebody was refueling a piece of construction equipment, and they spilled some fuel into the ditch. It was not a lot. There was, but it was enough to affect a couple of the gaskets. In the pipe that we had tested back in 1994, there was no problem with the gaskets. So it's a very limited area that was affected by this. So I think that's probably the explanation that I would go with on that. In the late 1970s, they probably weren't as careful with fueling equipment as they would be today in terms of environmental damage and all the rest of it. It was just a different world back then. When we looked at the water quality, we didn't find anything that was unexpected, I'll say, in terms of the water quality. There was a bit of biofilm on the pipe, which is not something that's not unexpected. So what happens in Edmonton is they have a unidirectional flushing program. In areas where the pipe material is cast iron, that flushing occurs annually. When you get to areas where the predominant material is PVC or asbestos cement, it's not very frequent at all because there's not the same issue and need to have the pipe flushed in order to maintain water quality. So the most recent flush in that area had been 3 years before. New areas with all PVC pipe in them typically are about 6 years between flushing intervals. As you can see, there wasn't a very big buildup on the pipe at all, and there was not much in there that was expected. Now, what are the implications of those failures that we talked about earlier? The flattening and the impact. When you've got existing pipe that's buried 8 feet below grade, it's got compacted, consolidated sand bedding around it. It's been basically sitting there pressurized, and so the pipe is kept in a circular position for almost all of the time that it's been there. And as the sand consolidates around it, it's holding that pipe in that shape. It's not going to, if you can drain the water out of it, it's still going to hold that circular shape. There's nothing going to happen. So concern about having the pipe flattening, I don't see that as any kind of a concern at that point in time. In terms of the impact, when the pipe is 8 feet in the ground, it's pretty hard for any kind of impact to be going on it that, other than somebody taking a directional drilling equipment and going and hitting it or something, but no pipe is intended to survive that. So again, I don't see those two failures as being a problem with PVC pipe. I don't see them as being a weakness or anything like that. Now, one question I did have was that when we'd done this direct tapping in 2017, we'd done it in the summertime. So I wanted to go back and I wanted to take a look at it in the wintertime. I wanted to see when the cold temperatures are there, when the water is much colder in the pipe, does that change the performance of that pipe at all? So we went back in February of 2018. We went back to the 6-inch diameter pipe, which is the smallest pipe, so that's the one that may be the most difficult one to tap successfully. And it was also the pipe group that had failed the cold impact test. So we went out, the air temperature was minus 2.2. The water in the pipe was at 35.8 degrees Fahrenheit, so it was still quite cold. The 25 millimeter tap under pressure, and that's a direct tap, and that was performed fine. Not a problem at all with it. This was just a pipe that was installed in 2016. It was to that historical park that I had alluded to in the beginning of the presentation, but it hadn't been connected to the park at that point in time. So the water in the pipe froze, and it deformed the pipe. So this is what it looked like when they pulled it out. You can see it's an oval shape on it. It's not looking very good. So because the crews knew that I like to test pipe, they cut out a piece for me, and we thawed it out. The thing is that they didn't give me a piece of pipe that was long enough to be a proper test for C900. So it was only 28 inches long. It should have been 36 inches long to be an official test for C900 standard. But we did take it back to the lab. Of course, the pipe retained its circular shape once the ice was thawed out. It met the quick burst requirement test, and it failed at just over 1,000 psi. So the material is very durable. We're going to go back to this cast iron pipe now. I remember I talked about 1965, where they decided to stop putting the pipe in. And so, excuse me, as time went on, the break rate went up. The pipe just kept failing, even though they weren't putting any more in. By 1985, the pipe was up to 1,600 breaks that year. All those breaks were starting to get to the point where the water utility was on the verge of bankruptcy. The operating costs of repairing all those breaks was really bad news. So City Council directed the water utility to come up with a solution to the cast iron water main break problem. And so in 1986, they started a replacement program. But because they didn't have any money, it had to be a pay-as-you-go program. So that meant everybody in the city got a surcharge put on their water bill, and they contributed to that. Whether they lived in a brand new subdivision that had PVC pipe or whether they were in an old area with cast iron, everybody paid the same rate. They set a standard for a replacement at 5 breaks per kilometer per year, which was about 3.1 breaks per mile per year. As time went on and they were able to get some of the break problems under control, the surcharge stayed in place. So we started looking at lower break rates. We started looking at hydraulics of the pipe. So if the pipe needed to be upsized in order to provide the current level of water demand in the area, that would be part of it. And also if there was road work occurring, we would be replacing pipe concurrent with that road work, so that they didn't replace a brand new road only to have us digging it up every little while. And then also in about 1994, 95, I started to add cathodic protection onto the iron pipe as well. I had learned of a system in southern Ontario where they were using a hydrovac and going down 8 feet with a hydrovac to get to the pipe, and then basically stud welding a wire onto that pipe and then dropping an anode down beside the pipe, and doing that at intervals depending on the different intervals depending on the diameter of the pipe. And so that also helped to reduce the number of breaks that were occurring. And also we did some work with internal lining where we were having problems with water quality. So we in fact, EPCOR had purchased a company in British Columbia that had an epoxy lining equipment. And so we brought that equipment to Edmonton and we used it to do lining on a number of cast iron pipes as well. So that peak in this graph is 1985. In terms of the number of breaks, you can see that the number of breaks have dropped down now. This is 2018 at the end of the graph. And you can see that the break rate has basically gone down to somewhere equal to what it was in the late 1950s. Now, I compared 3 pipe materials: asbestos cement, cast iron, and PVC. I did it in 3 different ways. I took the most recent 40 years, the years 15 to 20 after that pipe material became the predominant material in the installation system, and then the first 40 years as well, because PVC was 40 years old at that point in time. So the most recent 40 years, you can just see that with the iron pipe, we had almost 27,000 repairs, asbestos cement, about 1,000 repairs, and PVC, 168. Now there's, and you can see the lengths of the system for each of those materials as well in there too. So you can see that the breaks per mile on the PVC are much lower than the other materials, and that's consistent with Professor Barfus's information as well. When we look at the years 15 to 20, again, we see that the cast iron is leading the way, and the PVC pipe is very low in terms of the amount of problems with it. On the first 40 years, the story remains very similar in terms of the performance of these three different materials. So our experience is certainly consistent with the other utilities that contributed to Professor Barfus's reporting. So in conclusion, PVC pipe has provided exceptional performance in Edmonton for the 4 years up to 2018, and the system grew quite a bit between 95 and 2018. You can see that 6.4 excavations per year on the PVC pipe, that's not something that's too difficult for a water utility to handle. Minimal deterioration, and that was probably the most important thing that we picked up on. When we have an expectation of 100 years, our water rates are predicated on that expectation of 100 years of service. If we're not going to get 100 years of service, we'd better take a reevaluation of our water rates to make sure that we're actually funding the system properly. But at this point, we don't see any need to change that kind of thing. We're thinking 100 years is sort of our minimum expectation, and we'll take it from there. I won't certainly be around when they hit 100 years, and most of the people that are in the utility today won't be either. But we're not building it just for our time. We're building it for the long haul. Also, in terms of the maintenance aspect of things, the unidirectional flushing program, the more PVC pipe we have, the less costly that system is, because it doesn't have to be flushed as frequently. So that's a very positive thing. Edmonton has a very low leakage rate on their distribution system, and with over half of it being PVC, I'm sure that contributes to that low leakage rate. So back in 1977, the standard was 2 years old. It wasn't used anywhere else in Western Canada, so there was a little bit of risk, I would say, in Edmonton in trying the material. But as we get to today, there's minimal risk to zero risk, basically, in using PVC when compared to other available materials. And so that's really going to be the end of what I have to share with you today.